Sure. Thank you for having me again. Um, yeah, let me know if I'm not in a good position for the mic because I didn't realize I'm on the shorter side compared to this monitor. So I'll try to kind of peek around every once in a while. But if it cuts out, let me know. So yeah, I'm going to talk, closer to Earth, bring us into the magnetosphere. Um, and I thought I'd start by just introducing myself a teeny bit. I know a few of you, and I met a few of you at lunch, but I'm an assistant professor here at CU Boulder and a researcher at LASP. I am from New York, which came up, there was one, yeah, came up earlier this morning. I studied physics in undergrad and worked at Los Alamos before deciding I did want to keep going and get a PhD. And I actually got my PhD from the aerospace department here at CU, partly because I wanted to be building stuff, not just studying the physics, but I still, I think, consider myself a scientist, not an engineer. I moved around a fair amount after that. I spent some time at Berkeley and then at Goddard Space Flight Center, and then moved back here summer of 2020 to be a faculty member. So timing a pandemic was not intentional, but it was nice to be in Boulder during that time. And my research is primarily focused on Earth's magnetosphere, primarily studying energetic particle dynamics, so within Earth's radiation belts. But I've also started looking at other planetary magnetospheres, Jupiter, a little bit of Uranus, and then I also, in combination with the data analysis side of things, like to design and build instruments to measure energetic particles. Both from CubeSats or balloons. And so that's the picture on the far right. CubeSat project I was on, and then also a balloon campaign in Sodankala, Finland. And you'll see some of my, probably a fair amount of my biases coming into the content I chose to focus on in this talk, because this could be a semester class, the topic. And so I kind of am just doing the highlights, pretty high level, touching on things with probably a bias towards Earth's magnetosphere, and probably a little bit on the particle side rather than fields. But feel free to call me out on any of that if I'm leaving out your favorite part of the magnetosphere. And so, big picture overview of what I'll talk about. What are magnetospheres, right? What do they look like and how do they behave? And then I did, particularly for the theme of the summer school this year, but also always, I think we should always keep in mind, how do we know any of this? Where did we learn this? And, this goes beyond just learning about the magnetosphere, but any information you're ever presented with, whether it's from ChatGPT or somewhere online, you should always know, how do we know this? How do we trust this? How much do we believe this? What kinds of error bars are on this bit of knowledge? And I know you'll be hearing a lot about Heliophysics System Observatory later in the week. You'll probably see a lot of slides like this. And so I certainly have a kind of bias towards observations and spacecraft missions. But there's also, I think, other big component simulations and theory that help us understand the system too. So keep that in mind as we highlight different missions. It's often in combination with modelers and theorists that we're actually progressing our knowledge. Okay, so please interrupt me at any point. I will try to keep an eye out for hands waved. And then I know a lot of you have varied backgrounds and are experts in all sorts of different things. So my hope is you'll actually, learn as much, probably more from each other than from me, but this can start the conversation. And then I also wanted this to be an opportunity for you to kind of ask whatever silly questions you'd be embarrassed to ask somewhere else. I don't know you. Feel free to ask the most basic thing you can think of. Probably someone else is wondering also, even if you think it's something you should know coming from your area of expertise or your research area. And so I think last year someone was like, what are substorms? I study them, I study geomagnetic storms, but actually, what's the difference? And so we can have some of those conversations too, hopefully. Okay, and just for my own information, I kind of wanted to get a sense of where people are coming from, either your interests or current research. And so kind of solar, wind people. Okay, a lot of you. Okay. Earth's magnetosphere? A few. Okay. How about lower down? Ionosphere, atmosphere? A few. Okay. Other planets? Yeah, this is kind of broad, but and then I know this probably doesn't cover everything. Are there any other topics that people in the other category who you didn't feel like fit in well? Yeah. You want to share? Space dust. Yeah. Okay. Any others like technique based? I didn't know if there are people focused on a technique versus subject. Okay. Okay. Great. Thank you. A lot of solar wind. Yeah. Okay, so we can start with the very basic, what is a magnetosphere? How do we define it? And this is a definition I found. The volume of space from which the solar wind is excluded by a planet's magnetic field formed by the interaction of a flowing plasma with a magnetized body, right? Getting back to like very fundamental, what is this thing we will be referring to? I thought I'd check if everyone's happy with this definition or if we should modify it at all before moving forward. Yeah. Yeah, so what about unmagnetized planets? I know there's some Mars people in the room and some Venus people. Would you say that you study planetary magnetospheres? Yeah, yeah. Yes, I figured. So you can have an induced magnetosphere, right? Doesn't have to be the planet that has, an intrinsic strong magnetic field like Earth or Jupiter. And so any of these definitions we should definitely poke at and revise if and when needed. Yeah. Okay, but at Earth, we do have a strong internal magnetic field generated by dynamo processes in the core, right? And so when you're close to Earth, you can kind of treat the magnetic field that you're experiencing as something like a dipole or a multipole based on that internally generated field. But as you move further out, you are much more influenced by the medium that the Earth is sitting in. And so the solar wind tends to blunt one side of the magnetic field and stretch out the other. So the sunward side or the day side of the magnetosphere gets compressed, and then the nightward side gets stretched out in a big magnetotail. And it's because of this solar wind that we get a lot of the interesting dynamics and processes that we observe within Earth's magnetosphere. For scale, this picture is very much not to scale, right? The sun is not that close. But just to put some kind of common Earth orbits in there, low Earth orbit, very much within Earth's magnetosphere. The internally generated field describes it pretty well. As you move to geosynchronous orbit, which is sort of shown in that yellow, you're very often within Earth's magnetosphere, but during very extreme events, you might have that boundary come within your orbit. And it tends to, geostationary or geosynchronous orbit tends to be kind of on the boundary of more dipolar fields and much more stretched. So as you move beyond that distance, a dipolar magnetic field does not describe what you're sitting in very well. How about the moon? Where should we put the moon on this picture? Does anyone know? Inside the magnetosphere, outside? What distance? I'm hearing some insides. Yeah. Does anyone know what distance the moon sits at? Yeah. 60 Earth radii. And how about where this boundary on the day side of the magnetosphere is? 10-ish, yeah, 10 to 12, right? Yeah, depending on solar wind conditions. So the moon is kind of exciting because some of the time it is sitting in the upstream solar wind and sometimes it's deep within the magnetotail, right? And anyone know why I'm asking this? Why do we care about where the moon is? Unless you're a lunar scientist, sorry. Why would I care where the moon is as a magnetospheric physicist? I heard something back there. Hmm? Yeah, that's actually not what I was thinking of, but a great point in response that there have been very recent studies showing the effect of the tidal pull of the moon on low energy plasma within Earth's plasmasphere. Yeah. Any other reasons? You're trying to get funding, for example? So NASA is returning to the moon, right? We will be sending humans there, setting up long-term bases. This is both an opportunity to study the magnetosphere in more detail because you'll be flying through the magnetotail at relatively unprobed distances with all sorts of new instrumentation. And it's also, a reason why people might care what goes on in the magnetosphere. We should know what astronauts on the moon will be experiencing, what kinds of environments, both in the solar wind, but also as they cross through the tail. So I think that's a good thing to keep in mind. Okay, so we will walk through some of the main regions of the magnetosphere. This might be review again, but ask your silly questions or interrupt whenever. And one of the things I found recently was a paper in this a Frontiers article a few years ago. Does anyone know what this picture is of? Yeah, it's birds, right? Starlings. And when they group together like this, it's called a murmur or murmuration. Yeah, murmuration. Yeah. And so this article was really nice. It was kind of talking about complex systems and how, we can know the individual ingredients really well, an individual bird and its feathers, but how they move together and interact is much more complex, and they make these parallels between these formations and Earth's magnetosphere. I think it's good to keep in mind because as we study the magnetosphere, we often talk about all the little individual regions and terms, but they are all interacting and often in very complex ways. So even though you might know exactly what the solar wind is doing, how the magnetotail responds and how that affects the inner magnetosphere can be much more complex. I also like this paper because they kind of tongue-in-cheekly make a comment that both of these systems can disturb power grids. So these starlings have been known to land on power grids, and the sheer weight of all these birds can cause disruptions. And similarly, the magnetosphere disturbances there can cause geomagnetically induced currents and also disrupt the power grid. So if you have time, take a look at this paper. Okay, but we'll start at the very edge of the magnetosphere and actually beyond it, the bow shock, right? And so we have solar wind flowing in, it hits an obstacle, and we get a shock from that. What that bow shock looks like depends on the obstacle, right? So what properties of the obstacle do we care about if we want to know about the shock structure or shape or location? Density of the solar wind and what it's hitting. Uh-huh. Mm-hmm. Yeah. Is there a magnetic field to help produce that boundary, or is it going to hit the atmosphere, ionosphere, direct surface of the body? Yeah. Yeah. Any other things we care about? Yeah. The distance between the obstacle and the sun, and in what way does that affect the shock properties? I agree, but yeah. Any other ideas? Why would the distance matter? Yeah. Yeah. Absolutely. So size, yes, and do you have the angle of the magnetic field too? Yep. So whether you're coming in at the side like Earth or maybe at the poles. Distance, does any solar wind people know why distance of the planet from the sun is important for this shock? Yeah. Yeah, absolutely. So we want to know the incoming solar wind properties, and those vary, or some of them vary depending on your distance from the source. Yeah, yeah. Yes, whether you will get a shock or not. Yeah. 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 So that speed matters a lot. Okay, I think we talked about most of these. Yes, is it magnetized? What's the configuration of the magnetic field? The Mach number of the solar wind. So that relates to some of those properties and how they vary from distance. Yeah. Yeah, absolutely. So what kind of atmosphere you're actually impacting? If you don't have a magnetic field to produce the barrier, what does the atmosphere look like? Yeah, excellent. Okay, wonderful. Okay, and here's just pretty pictures of examples of how that shape of the object really does make a difference, right? We have beautiful models to show us some of these interactions, and we can plug in different planets and different properties. This is Earth, and you can see that at least at Earth, the magnetosheath region, which is that shocked solar wind, is denser, hotter, and slower than the pristine solar wind upstream. And as the solar wind flows around the sides of the planet, the flanks, it then expands, cools, and speeds up again. Okay, so you can see, hotter, denser, and this one's hard to see because zero, it's positive and negative, but slower is that kind of teal color. Yeah. These are pretty models. This is, our basic shock physics. But what the system actually looks like can be much more complex, right? There's a lot of structure and variability within the magnetosheath. And I think the reasons we might care about the magnetosheath as a magnetospheric physicist is that, what we see in the upstream solar wind isn't actually what's directly interacting with our magnetosphere. And so any localized irregularities or structures are actually might make a big difference in how that boundary actually changes in time and space. And then also, the sheath is not uniform. There's lots of current work these days into kind of local dayside transients and structure and substructure. Okay, so if we wanted to study the sheath, right, we might want to put a spacecraft that would like sit out there, yeah, and probe it. Yeah, does anyone study the magnetosheath? Oh yeah, okay, great. From a data side or, okay, modeling? Okay, and you're, yes? What kinds of observations do you use? Ah, okay. Okay, but the sheath on Mars, perfect, great example. Okay, so you might want this at Mars. And if you really want to get at the substructure and variability in space, some of these more localized features, you might want more than one, right? And so missions like MMS and Themis have been doing a great job providing this type of data set here at Earth. And I know every time I talk about Earth, I'm very privileged to have all the data I do have, and other planets have to make do with a lot less information. Okay, so moving in, that's still outside the magnetosphere, right? It's just what is shaping and changing the magnetosphere. So we get to the boundary, magnetopause. You may have learned how we figure out where that boundary is, right? It's from pressure balance, pressure in the solar wind versus pressure inside. And at least at Earth, we can simplify this equation and say that the solar wind pressure is dominated by the dynamic pressure, the flow pressure. And within the magnetosphere, the pressure at these distances is dominated by the magnetic field pressure. And you can, to first order, get the location of the magnetopause through this by ignoring some of these smaller terms. Do we know this is right? How do we know we can ignore terms? Have we looked at this, Earth's magnetopause? Probably, right? Yeah. Yeah. So we have lots of different missions that have measured the location of the magnetopause, flown across it back and forth, or sat out there and had it flap across the location. Here are data from MMS, Themis, and Cluster spacecraft, all kind of tracking that magnetopause location. And then I don't know if any of you have used the Shu et al. Model. I use it kind of daily to estimate where the magnetopause might be, to like very rough first approximation. And it's an empirical model. So it's not based on physics, but it's based on collecting all these observations, all these magnetopause crossings, and trying to fit different equations to them under different solar wind driving. And it actually does a pretty good job. Yeah, these empirical models, if you feed them enough data, they're pretty good. Okay, and I think the cartoon picture of that magnetopause boundary sometimes is misleading, because this bubble carved out of the solar wind is not really a bubble, right? It's full of stuff. It's not empty. It's full of primarily charged particles, plasma, ions, electrons, right? Ranging in energy from very low energy, electron volts, up to mega electron volts, super high energy. And they flow in different regions, and each have their own, little terminology and names. But I think the main takeaway is that there's all sorts of plasma filling Earth's magnetosphere, and that's partly why it's interesting. Where do these particles come from, if we have that boundary? Anyone, any magnetospheric people know? Where is the plasma within the magnetosphere coming from originally? Solar wind. Any other? What's that? Yeah, so the solar wind is one source. Any other sources of particles in the magnetosphere? Yeah, so we have this nice thick atmosphere that can get ionized, turn into the ionosphere, and then get energized and actually escape. And so the two primary sources of particles within the magnetosphere, I think often we forget about the atmosphere ionosphere and think it's all solar wind, but our own planet is a major source of plasma within the magnetosphere. And this is a pretty active area of study of relative importance of these two sources, which one dominates when and where. I thought I'd check. So, we could model where the particles are coming from, right? How do we actually know where this electron in the magnetosphere came from? Was it the sun or Earth's atmosphere? So energy is one thing we could check. And if it's low energy, we might think from Earth. Higher energy, you might think solar wind, right? One of the things this cartoon does show is that the particles are moving around and circulating, though. And so even if a particle starts as low energy, it leaves Earth's atmosphere, escapes. As it circulates through the magnetosphere, it can be acted upon by many different energization processes. And so by energy alone, you might not know exactly where the particle came from. If it's been circulating for a while and different acceleration mechanisms within the magnetosphere have changed its energy, right? Yeah. Yeah, so there might be some variability based on if you're on the sunward side versus deep in the tail. Is that what you're saying? Yeah, there are definitely that ratio and relative abundance of both varies significantly spatially throughout the magnetosphere. Yeah. Composition, yeah. So what could you learn from composition? Like ion. Yeah, so ion composition is one of the primary ways we actually try to track where these particles came from. So the electrons, you may not know. An electron is an electron, and if its energy has changed because of all these processes acting on it, and if it's moved through the system, maybe it started on the day side but has circulated throughout, you might have lost track of where it came from. But ions are a great way as tracers of plasma because, like you said, certain ion species are more likely from Earth's atmosphere, ionosphere, things like nitrogen, Whereas other ones, like alpha particles, helium double plus, or highly ionized oxygen, might be tracers that only the sun would produce. And so ion composition as well as charge state can give us a lot of insight into where these particles came from and what role the solar wind versus atmosphere is playing in the source of the plasma within the magnetosphere. The gaps in these data. Yeah. So this is a plot I stole because it had different ions on it. And it's from a series of papers studying this kind of relative abundance. I should have checked what I think it's based on the location of the spacecraft and that they're trying to get solar wind measurements here, ionospheric ones here, and they're only looking within the magnetosphere. And so if the satellite is moving and comes really close to the atmosphere or goes beyond the magnetopause, they cut those sections out. It might also just be those pesky data gaps that we get in real data. But I think it's because of the regularity of it, I think it's actually due to location of the spacecraft. They were trying to remove that as a variable and just look in a similar spot at how the composition varied, I think. Yeah, yeah. Okay, so this is from a series of papers by Lynn Kistler, who's done a lot of work on using ion composition and charge state to actually track when the solar wind is a larger kind of source of the plasma we measure within the magnetosphere and how that varies based on time and space and things like that. And if you get these ion fractions, you can kind of infer something about the electrons and the total plasma sources. Okay, so speaking of plasma, right? You'll hear a lot of different terms for different regions of plasma within the magnetosphere. The plasma sheet, which tends to be equatorial-ish on the night side and the tail. The plasma sphere, which is very close to Earth, very low energy, dense, sourced by the atmosphere ionosphere. This cartoon isn't a great one because they're Van Allen radiation belts. They couldn't really stick them in the picture, but they'd sit, somewhere in here, right? If you could insert them, those are higher energy particles, electrons, ions, very high energy. This picture sort of shows things a little bit better. We often categorize these particle populations both by energy as well as location. And so this tries to depict them all kind of in the inner magnetosphere, they tend to overlap. You can't necessarily say this is just where the ring current sits, and this is just the radiation belts, and this is just the plasmasphere. And so then if you're in a location where they all overlap, you might look at the energies. And so lowest energy, coldest plasma in the plasmasphere close to Earth. As you move out, you get a kind of kiloelectron volt plasma, ions and electrons in the ring current. And then as you move up in energy even further into the mega electron volts, you're getting into the radiation belts. But these really sit kind of right on top of the ring current in here. Yeah? Okay. Since this is the kind of high level picture, I didn't want to go into more detail than this. But there's a few other graphics I thought sort of show some of these different populations. And I like this one because it shows temperature or energy on the y-axis versus density of all these different populations. And so now instead of sorting by space and spatial region, we're sorting by these properties. And you can see there's really a wide range of energies the plasma spans, right? Orders of magnitude, as well as a very wide range of densities. Highest energies tend to be less dense, but still important for other reasons, whereas kind of the mass density of the system tends to be dominated by the colder, lower energy populations. This is interesting, but it's also makes life trickier for those of us who want to measure these populations. And so if you want to build an instrument to measure particles within the magnetosphere, you have to span orders of magnitude in flux and in energy. Now we've swapped the axes, but similar idea, right? And so often what you do is you have to kind of piece together different particle instruments, some focused more on low energy particles that can handle higher densities or fluxes. And then you have another one that can do the in-between, and then the higher energies, lower fluxes. And this is an example from the MAGICE instruments on the Van Allen probe spacecraft, where they were trying to measure kind of low KeV up through MeV electrons, and had to do it with 3 different instruments. And this is actually just one instrument suite on the Van Allen probes, and there's actually another one, the REPT instrument, that does even higher energies, and another one, HOPE, that does even lower energies. And so, yeah, from a spacecraft perspective, this makes it challenging if you don't know the typical densities or energies you're going to try to measure. Yeah, did you? Yeah. Yeah, so where do the high energy particles in the radiation belts come from? One of the responses already, the solar wind, is correct. Those particles can come initially from the solar wind, enter into the magnetosphere. But then, like some of those cartoons showed, they get circulated about. And so there are a lot of local energization processes local to the magnetosphere itself, plasma waves and wave particle interactions that can really energize electrons and ions in the system. And so a lot of the electrons in Earth's radiation belt, for example, get energized by plasma waves and could have been from the solar wind or a lower energy source initially. So yeah, I think people often assume it's a high energy particle directly from the sun that then gets trapped in Earth's magnetic field, but there's a lot of processing and energization or energy loss that can happen to the particles once they're in there. Yeah, good question. Any other question? Okay. So yeah, this is both interesting, but a major challenge for people building instruments to measure this, this environment. And it gets even more complicated if we care about not just the magnetospheric plasma, but for example, if you want to know the solar wind properties plus the magnetosheath plus magnetosphere, these again are just 2 examples, ions and electrons, of fluxes versus energy. And you can see just how wide a range there are. And so that cartoon of studying Earth's magnetosheath, if you're on an orbit that crosses the magnetosphere and the solar wind, and you really want to know about all the different properties along the way, you have to often carry a large instrument suite with you. And then I've talked a lot about particles. Waves are also very important, plasma waves, and the magnetosphere is kind of home to a whole host of them. This is just a single example of from the CRESS spacecraft that cut kind of close to the Earth out through the radiation belts and back. And so you can see as the spacecraft moves away from Earth, you get all sorts of waves lighting up and different ones as it moves back closer to Earth. And these plasma waves are critical for energizing particles in the radiation belts or scattering them into Earth's atmosphere. And you know, this plot is often shown to point to kind of the zoo of waves that occur in the magnetosphere. And there's, you know, each one has its own different name, which I'm not going to go through and make you memorize, but I did want to at least do some justice to the plasma wave environment, not just particle environment within the magnetosphere, and how varied and complex it is. And I know you'll also have many talks about lower down, I think tomorrow. So I'm kind of skipping that too. I'm pretending geospace environment is really my favorite area of geospace, the magnetosphere. But as you move closer to Earth, you get into the denser regions. You can no longer kind of assume a collisionless plasma, and you really have to pay attention to the role of neutrals and ions and collisions and things like that. So things get much more complex, or well, equally complex, I'd say. Yeah. But I think you'll hear more from Bob Marshall about that. Okay, so that's the static picture we have of the magnetosphere. I thought I'd just pause. Questions about jargon and whatever I threw out? Yeah. Mm-hmm. Yeah, so within Earth's magnetosphere, I was pointing out the plasma sheet, but you're right, there is a current sheet in that magnetotail because the magnetic fields are going from, stretched in one direction, crossing, and stretched in the other. So there is also a current sheet. Um, they overlap in space and are tied to the same kind of physical phenomena because of that kink in Earth's magnetic field and the stretching of the tail. Um, People sometimes talk about things in a currents way versus a particles way. And so if you are tracking particles, you might say, okay, they're most dense here. And so that's the plasma sheet. If you're looking at currents generated by magnetic fields, you would see that the magnetic field changes direction in that region and say, okay, there's a current sheet there. They aren't technically the same because one is plasma and one is a currents generated by the magnetic field, but they are in that same region and highly related to each other because plasma follows magnetic fields. Yeah, yeah. Yeah, let's see. I have trouble getting 3D pictures of the system that I like. Um, it's kind of a sheet because if you could picture this stretching out and in 3D. So we're looking at the side of it, but if you rotate it around, as you move to the night side, you get like almost like a tongue shape stretching down. Like it has some thickness, it has some width across the tail, but it's not a cylinder, right? It's a little more flattened. So sheet is, you know, like a thick sheet, maybe a blanket. Yeah, yeah, great question. Yeah. Anything else? Okay, should we move on to the more fun picture? So this is the static picture, all the components, but the system is highly dynamic, right? It's not staying there fixed in time and space. Um, the system is varying in time and space, often due to that solar wind driver, right? Which, you learned about this morning. And so that solar wind driver is not constant, and that translates into magnetospheric dynamics. And we get, particles spanning orders of magnitude in energy, waves spanning orders of magnitude in frequency, and then the system also responding on timescales from seconds, minutes to years. And so, you might have a shock in the solar wind that causes a pretty instantaneous response in the magnetosphere, or you might have, variability on solar cycle type timeframes that translates to solar cycle type patterns you would find in the magnetospheric composition dynamics, things like that. So that's partly, I think, why I like the system, that you can study it on this very wide range of scales. Geomagnetic activity, right? This is one of the main drivers of that variability within the magnetosphere. Geomagnetic storms are these kind of temporary but often lasting days to a week disturbances of the magnetosphere, typically caused by things in the solar wind, right? CMEs, high-speed streams. Whereas substorms tend to be shorter lived on the order of hours, more frequent, and more localized disturbances to the magnetosphere. And this plot on the bottom, does anyone know what I'm showing here? We're looking at one of the measures we use to show a geomagnetic storm, and it's the DST index. And so we're measuring it with magnetometers on the surface of the Earth. We measure the magnetic field strength in a distributed array of magnetometers. And we know in kind of a background, quiet, steady state, what that magnetic field strength should be. And when it gets disturbed, the magnetic field strength will change. And so what you often see, what you would typically see during a geomagnetic storm, is an initial increase in the magnetic field strength based on that compression of whatever's hitting the system. And then you see this big decrease, which is particles that get circulated through the magnetotail, they convect into the inner magnetosphere and cause a current system, the ring current, to form. And a current generates a magnetic field, right? And so that ring current generates a magnetic field that's opposite Earth's dipole. And so you would see a large negative large negative magnetic field during a geomagnetic storm, and then it slowly recovers. Yeah. DST is what we often point to for geomagnetic activity, but what about KP, AE, AP, AL? There's like, SINH, alphabet soup of different things people use to indicate geomagnetic activity. Does anyone know the difference between all of these? Which ones you should use when, what they are indicating? Mm-hmm. Mm-hmm. Yeah. Yeah. And did you have something to add to or same? Okay. Yeah. So here's a maybe you can't see it at all. There used to be gray shading on this that's very faint. DST is measured by these ground stations very close to the equator. And so you need a much larger, more global disturbance to actually affect the magnetic field measurements near the equator. Whereas KP stations are these mid latitudes, and then AE stations are there's a really faint gray swath at the higher latitudes. So they're all measures of magnetic field deflections from Earth's nominal system, but measured at different latitudes. And so you could say, okay, who cares? These are just different ways we measure disturbances, but they do relate to kind of the physical phenomenon happening in the magnetosphere and what you're actually probing. And so AE at the highest latitudes tends to respond to any little disturbance in the tail. So it maps to further out in the magnetosphere. And so substorm activity, for example, which is more localized to the night side and at higher latitudes, might show up in an AE index. Whereas if you have to disturb the magnetic field all the way at the equator, you need a much more global, larger disturbance. And so DST is actually kind of measuring a slightly different current system that gets set up in Earth's magnetosphere in a different location. And so how we measure these things is always nice to keep in mind as we often use these indices kind of to make correlations, make big statistical relationships between things, but what's actually causing the measurement to change, and how should we interpret it in terms of magnetospheric dynamics is good to keep in mind. Okay, I don't know if okay, so here's the cartoon, right? This is the disturbed magnetosphere. Something from the sun erupts and moves earthward. It hits our magnetic shield, our bubble protecting us, causes compression on the day side, stretches out the night side. It might cause magnetic reconnection that you're seeing in there with the magic white flashes, which cause particles to stream along the magnetic field and induces in aurora that we see, right? So geomagnetic activity, and we'll see aurora and we think, wow, it's amazing, right? So that plasma entry of the solar wind can happen two ways, right? On the day side, if you have a CME that impacts and you have a southward magnetic field, you can get reconnection, which I think you'll talk about in much more on the plasma physics side. But the cartoon version is a kind of breaking of the magnetic field lines and opening up of Earth's magnetic system and kind of direct access of solar wind into the system. Whereas you can also have Kelvin-Helmholtz instabilities, which is really just kind of shear flow along the flanks, right? You're having a flow go past this obstacle, and you can set up instabilities that particles can actually enter through the sides of the system as well. The cartoon of the magnetic fields peeling away is often called the Dungy cycle. And there's the video version that I showed, and then there's these, screenshots of the system and how the magnetic field lines peel away. These magnetic field lines aren't real, right? They're how we draw the magnetosphere in space, but it's not like there's a physical line that you snip and tie. But it's kind of the best way we can show it. And so you get the reconnection on the day side, the rejoining, so opening of these magnetic field lines that have one foot point at Earth and one now in the solar wind. They get peeled back into the magnetotail, build up back there until there's enough build up that they can reconnect again and cause a plasmoid to move both inward and outward. Yeah, so that's the Dungy cycle cartoon, and that's what's happening during a geomagnetic storm. There's a lot of kind of nuance to that and details that cartoon glosses over. And so the Themis mission, for example, tried to probe what's actually happening in the magnetotail during substorms and storm activity. And are we getting that clean kind of single reconnection point and a moving inward of plasma through the tail and then a plasmoid ejected out the back? Or might you also have near Earth reconnection lines that are sending plasma both towards Earth and then away, in addition to distant tail reconnection, right? And so the picture always gets more complicated beyond the pretty cartoon. And so they tried to probe which one of these is happening by having 5 spacecraft lined up at different distances within the magnetotail, right? To see if flows are moving inward or outward at that location. And you could kind of try to figure out, if you're here, are you measuring flows inward or outward? And does that mean the reconnection line is within you or beyond you? Oh. And then just as a reminder, again, there's lots of complex current systems within the magnetosphere. All these moving magnetic fields set up currents, right? And so you can get a cross-tail current. You also have a lot of these current systems closing at low altitude, so in the ionosphere. And so you're getting kind of a coupling between magnetotail dynamics and what you see in the ionosphere or with aurora. And so often the aurora is used to kind of look at tail dynamics because it's almost a map or a projection of all those current systems that have to close somewhere. And so it's kind of the one part of the magnetosphere that we have pretty pictures of also, compared to the solar physicists who show beautiful images. Aurora tends to be what I point to sell magnetospheric physics to people beyond the field, right? But it is really, evidence of further dynamics within the magnetosphere that are kind of current systems that are closing at low altitude. Did any of you see aurora? Who's seen aurora? Yeah, from where? Norway, Alaska, anywhere? Yeah. Oh, Karuna. Yeah. Okay. Yeah. Boston. Yeah. Was it this past May? Yeah. Oh, nice. Okay. Yeah. So aurora is also the one way that we can kind of connect to people who don't study magnetospheric physics, who may have actually observed it and then start to wonder what's causing this, right? And so there's a great, I don't know if it'll play, video that a researcher in my group took from here in Boulder during that big May storm in 2024. And it didn't look this great in person, I will say. By eye, it was a little less exciting, but he set up a tripod and stuff and captured really cool aurora. Okay, so why I like the aurora, it helps connect us to the public, and it's a way to kind of sell magnetospheric physics. It's also one of the earlier observations we had to try to understand the system. And so these are kind of famous little drawings by Akasofu of auroral structures and arcs and how they changed in time. And some of the earlier studies of substorm activity in the magnetosphere come from these little hand-drawn drawings. And so I like that as a way to study the system before we had advanced spacecraft and instrumentation for those spacecraft. You could just kind of look up and get your sketchbook. And then the other reason it's great is because we also see aurora at other planets. And so if we can understand what's causing the aurora here at Earth, what dynamics in the magnetosphere cause different auroral arc structures and changes, we can use some of the auroral images we have at other planets that lack comprehensive magnetospheric missions and try to figure out what's going on there too. Yeah. Yeah, so Jupiter has an auroral oval similar to Earth's, but it also has many moons embedded within the system, and some which are strong plasma sources. And so they actually generate current systems between the moon, this plasma, and the ionosphere of the planet. And you get auroral footprints of these moons, and they can actually be used to help map, where the structures you're observing in the aurora are to where in the magnetosphere they're generated, because you know the exact location of the moon, for example. And so they're kind of a natural mapping technique to figure out where the aurora is coming from in the magnetosphere, which is kind of cool. There have been, concept studies here at Earth of like, could you make a laser beam or a kind of electron gun, fly it through the magnetosphere and cause a little auroral footprint so that you could really better map structures you see down at low altitude to the tail and where they're coming from. So, could you make an IO at Earth? Yeah. And just because I saw that there were some Mars people, I'm not just going to highlight magnetized planets, but Mars, of course, also has pretty complex, amazing aurora that recent missions are revealing all the different types and generation mechanisms of. Okay, and then I just did want to put a few slides in here about the time scales. So we've looked at kind of geomagnetic storm and substorm time scales, hours to days. And so those can cause dynamics in the magnetic field, the aurora, current systems, also the radiation belts. And so this is where my research is focused. And so here we're looking at kind of a radial slice outward on the y-axis through energetic particles, so close to Earth and further away, in units of Earth radii, sort of, over time, over a few week period. And the color is the intensity or flux of these high energy, very high energy, 4.5 mega electron volt electrons in the Earth's radiation belts. And during this period, there are 3 geomagnetic storms that you see in this DST index on the bottom, or 4 actually. And you can see that each one really causes a pretty dramatically different response to the outer radiation belt. So this is kind of one of the active areas of study, as we on paper know how the magnetosphere responds to a CME or a geomagnetic storm, but can we actually predict what will happen to the radiation belts? And the answer is no. And the answer is that the response can be highly varied depending on a lot of different other parameters. So just looking at the strength of a geomagnetic storm or just looking at the solar wind drivers alone, it's very difficult to know if the radiation belts will get enhanced by orders of magnitude within hours or totally disappear, kind of get depleted and removed from the magnetospheric system again within hours. So this is one of the challenges of radiation belt physics, but also magnetospheric studies. And then, so this is on the kind of geomagnetic storm time scale, but if we look now on the decades time scale, so we're looking at years on the bottom here, 20 years of data, again, kind of radial distance, radial cut outward through the radiation belts. Now we're just looking at the outer belt. And on the top, you can see the solar cycle sunspot number as well as solar wind speed. And if we add on here the kind of running average of DST, you can see it tracks pretty well with the particle intensity and location of the outer radiation belt. And so when we study Earth's radiation belts, we also are looking at decade time scales and seeing that there was this very depleted few years, actually, that maps to a very prolonged solar minimum, low solar wind speeds, as well as more enhanced periods during periods of higher solar activity. So a lot of radiation belt studies are both on the hours to days timescales as well as the seasonal and annual and solar cycle timescales. Okay. Um, okay, any questions about this part, dynamics? Yeah. Yeah. So how would you know if it's happening in that near Earth reconnection versus deeper in the tail? That is a great question. I think if we knew, we would be able to better understand why it's happening and where. I don't have a great answer. Does anyone? Is anyone in the room have a great answer for this? No, I would say the a lot of this stuff is the term preconditioning is used a fair amount. So understanding what happened to the system before and how it might have pumped up the plasma sheet or changed its composition or density or things like that. At least for radiation belt studies, you know, whether you had 2 geomagnetic storms in a row versus a long period of quiet and then something means that the response is often different. So I think in the magnetotail, the same is true, that knowing the time history of what has happened and not just what's instantaneously happening can help. But I think it's still a pretty big unknown unless someone in the room corrects me. Yeah. Okay. Yeah. Yeah, great question. Other questions on dynamics? Yeah. Yeah. Mm, yeah. So Uh, some aurora has these beautiful curtains. There's also kind of diffuse speckly aurora that's not what you used to sell to people, but also interesting. But the aurora that's happening in a curtain, you are seeing emissions at different altitudes. And these are current sheets. And so you are getting emissions based on, you know, if you made that cartoon of the magnetic field lines and made it 3D, you would get kind of ribbons of changes in the magnetic field that are moving inward and streams of electrons in kind of ribbon shapes coming in to Earth's atmosphere and then exciting things at different altitudes. So you're getting the vertical structure from looking at different altitudes, and then that uh, the thinness of it because it is a current sheet. Yeah, and then the width of that ribbon is based on whatever is happening in the tail. So like in this example, this maybe shows kind of why you'd see a ribbon in the ionosphere. If you have a current system in the tail and this is closing at low altitudes, you get some width across the tail, which varies depending on what's happening, and then some height based on the emissions, and then it's pretty thin. I don't know if that helps. Not really. You're like, not at all. Okay. Other questions? Yeah. It's the magnetic field in space as well, but we can measure it with ground-based magnetometers. So any change of the magnetic field in space also maps to a change in the magnetic field strength at the Earth. Because if you change this part of a magnetic field line, it'll also change, you know, you wiggle this part of the rubber band and this part is attached. Mhm. Okay. So here, yeah, it's that uh that's okay. Maybe others did too. I don't know. But yeah, I guess are you wondering if the magnetic field in space is changing or just on the ground? And that's what we're measuring? Yeah, so you're measuring the constant magnetic field from Earth's internal dynamo, but you're also measuring changes to the magnetic field induced by solar wind variability or currents within the magnetosphere. And so this value that you see here, this, 100 nanotesla, is what you might measure as the deflection of the magnetic field strength at the surface of the Earth. Does anyone know order of magnitude what the magnetic field strength of like Earth's dipole is at the surface of the Earth? Uh, yeah, of course, I know this in nanotesla, so I should specify units also. Yeah, so uh, like tens of thousands of nanotesla. Yeah. Yeah. And so that's why we often subtract out the background field, because if you were just looking at the strength, the raw measurement of magnetic field strength, it would be dominated by that constant of Earth's field. But once you subtract that out, you can measure these kind of tens of nanotesla variations in that. Yeah. 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 Yeah, so DST typically might not respond to smaller substorm activity. It might not even trigger a current system that could be measured at the equator, only currents at high latitudes. So if you're measuring DST and it has a big deflection like this, it indicates a geomagnetic storm. If you see little wiggles in it, you might not know, it's not constant. If you were looking at the AE index, for example, at high latitudes, you would definitely see substorm activity, but you would also tend to see a lot of substorm activity during geomagnetic storms. So there it would be much trickier to kind of figure out what you're looking at from AE alone. You kind of want to combine all the measurements and say, okay, there's substorm activity as measured by AE, but we also see a disturbance in DST. So this is a big one, a storm. Whereas if it's only the more localized, you might not see it here. Yeah. Yeah, you're right. I skipped the cusp. Absolutely. Yeah, here, maybe we can look at it here. In theory, yes, even without reconnection on the of these field lines, you could have solar wind entry pretty low in altitude directly in the cusp region. How it gets into the system from there, though, like if if you looked in that region, it's still not necessarily going to enter the magnetosphere just because it gets in the cusp. So you need other processes that can kind of take it from the cusp into the circulation pattern. And so often that means reconnection somewhere along the magnetic field to get it onto those closed field lines from the open solar wind. Yeah, yeah. Yeah, like if you flew a spacecraft through this, across the pole, you'd see closed fields, right? And then you'd probably see closed fields again, but from the other side, very close to each other. Uh-huh. But you might have different plasma or particle populations entering in that as you move from one to the other. Yeah. Unless you do have reconnection, which is kind of opening up that polar cap. And so then you have magnetic field lines that have one foot point at Earth and one to the solar wind. And so if you have um, a large amount of reconnection, you'd open up that polar cap and you'd have more open field lines in between the two closed systems. Yeah, so kind of depends on your geometry and your assumptions about the dynamics that are going on. But it is why measurements of the cusp can tell you a lot about how the system is connecting or opening up or not. Yeah. Do you have a question too? Yeah. Yeah, yeah. Yeah, this is a great question. These are like um, go back decades, and they are built off of a certain number of ground stations. And I don't know the numbers. I think DST is at least 4 based on this picture. Does anyone else know? I know the SIMH index, you get higher time resolution, and it also has, you can get that because you have more ground stations that go into it. And so, uh, yeah, you can build different time resolutions based on the number of stations you'd have. But I don't know if they just try to add more or they keep it fixed so that it's a constant over time and you can cross compare. Yeah, no one's correcting me here. Okay, unknown. Yeah. Mm-hmm. Yeah, how deep in altitude can it go? That's a great question. I believe it can go pretty deep because missions like Tracers that just launched are flying at low altitude, kind of hundreds of kilometers, and going to cut through the cusp. So it can reach pretty low, which means you have kind of direct access to that system. Yeah. Hmm. Yeah, good question. Yeah, because from these cartoons, it's really hard to tell. Yeah. Okay. Any other questions here? We'll keep going. We'll see if, yeah, yeah. Yeah, I think what you would want is yes, an even distribution. What happens in reality is not that because you have land masses in certain spots and some regions are easier to access or more open to having these stations. And so you don't necessarily have what you would draw on paper of the system you would want to measure these things. But I think they do try to get some distribution so that you don't have a big gap in space or at certain longitudes. Yeah. Yeah. Okay, then let's move forward. I thought we'd take a few minutes. I think we have 15 minutes left. Yeah, 10? I don't know what, 10-ish. Okay. Um, I thought we'd do a little experiment, group exercise. So say we wanted to measure plasma entry from the magnetotail to the inner magnetosphere, right? That kind of that question you asked of where is the reconnection happening and how does that translate to energy and mass flow from the tail into the inner magnetosphere. And so I thought we'd kind of think about if we wanted to study this system, what type of mission might you design to actually probe this region and better understand um, mass and energy transport from the tail to the inner magnetosphere. And this is a simulation of the magnetotail that actually tries to show that three-dimensional structure a little better. Now we're looking down on the Earth, and what you can see is it's not constant uniform across the whole tail. There's all sorts of little things called bursty bulk flows, mesoscale structures, fingers that reach in, reconnection that happens in a more localized region, not across the whole tail, and causes particles to move earthward. And so the system is pretty complex. And so I thought, let's take 5 minutes, talk at your tables about, what kind of mission might you want to design to study this system.
Just trying to think about where Geospace is. Oh, I don't know what Geospace, I don't know what that's at.
Okay. Let's bring it back up here. I want to hear all your wonderful mission concepts. Even if they're perfect. Okay, I can also repeat stuff if it's hard to hear. So yeah, did anyone come up with ideas of how to probe this kind of magnetotail intermagnetosphere transition region and its structure?
Oh, am I? Yeah. Who wants to write a proposal to living with a star?
Yeah, I'm gonna take notes.
Yeah, okay. They're deep in conversation over there. So who's got something?
There's no wrong answer.
You want to
I mean, there's no
propose your
right
Dyson
answers either.
sphere
Yeah.
for the Earth? No. Okay.
Yeah, just talk through where you might start.
Yeah.
Yep, perfect.
Well, we don't know what our budget is.
No
but
budget. I mean, infinite. Let's not
Can
be
actually-
constrained by realism yet.
I'd like to have maybe not in like not geosynchronous, but in that plane, something that's always in the night side, something always in the day side. So we'd have to have some number of satellites in an orbit in that position, so that one's always guaranteed there. We could
Yep.
take advantage of Lagrange points. I don't know Lagrange point past Earth. I'm not sure how far that is in the magnetotail though.
Yeah, pretty
too
far.
far.
Pretty
Okay.
far. Yeah.
But at least we could use what L1 between Sun and Earth. And then that would at least give us an idea of what's coming in.
What's coming in? Yeah. Yeah. So lots of spacecraft distributed in both local time, kind of sunward, nightward. Yeah. And how about back there? Yeah. Oh, did you have a hand up? Yeah. Same thing. Okay. Yeah.
We were also thinking of having a wide range for the energy coverage and a high resolution for
Mhm.
the instruments. And one another thing, but we are not sure if it's if it would be a good idea or not, having an instrument for the energetic neutral particles in this area.
Hmm. Yeah, you kind of want to measure all the things everywhere. Is that, yeah, what I'm hearing? Because we're unconstrained by budget.
in a good resolution.
Mm-hmm. Yeah, yeah. Any other solutions?
Budget.
Yeah, yeah.
I don't know if I have a solution, because it kind of sounds like we have similar ideas.
Okay.
I just had a question. Is there technically like an emission spectra, since there is, like excited
Yeah.
particles that are
Yeah, so
emitting?
that's a great question. Could you kind of image it? Is it emitting?
Right, like, or
Yeah.
just like to get a spectra of,
Yep.
I don't know, known lines.
Yeah, so not in the kind of way you might be imagining, but there are instruments called energetic neutral particle imagers. And so you do get emission of energetic neutrals from interactions with the plasma in this environment. And you can make maps of those to try to understand kind of image the system instead of point measurements. Yeah.
So that would be like from specific sets of filters that you would just take.
Yeah, in this case, it's measuring different energy ranges
Right,
of
okay.
particles, but same thing, right? Same energy of photons versus particles, of neutrals. Yeah, yeah, yeah. Hmm.
Sorry.
Not sure if I'm just thinking of two spacecrafts, one orbiting this way
Hmm.
and another orbiting this way.
Hmm.
Uh, I don't know if this orbit would give information about the magnetic reconnection side,
Hmm.
and this orbit will give information about the particles that are funneling into the.
Yeah, so you kind of want something, you're talking 3D, something across the tail and then coming out of the plane, looking
Yeah.
at what's coming in and out. Hmm.
Not sure how is this exactly happening, but
Yeah.
yeah.
Yeah, yeah, yeah. Any other ideas people came up with that haven't been talked about yet? Okay, so I asked this question because there have been a number of recent mission concepts trying to get at this science, some of which are very similar to what has been discussed here. So this MagCon concept has been around for a while, and it basically says we want all the measurements everywhere, right? Fill the magnetosphere with spacecraft, get radial distances, range of local times, range of inclinations, and understand what the system is doing. There have been slightly more realistic versions of that proposed too, that kind of laid out different numbers of spacecraft and orbit parameters that you could try to, constrain. But there are two other ones that are kind of more different ways at approaching it. And one is very similar to kind of imaging the tail. That was this Paragon concept that said, let's fly an energetic neutral atom imager, and it'll be in a high altitude orbit, polar orbit above the Earth, and then kind of look down tail and image the emissions from that system. And if you have high enough image resolution, you could see some of this substructure. And then the last way is the cinema mission concept is a small explorer, so kind of more budget constrained, but said kind of, can we probe the magnetotail from low altitude? All these magnetic field lines are mapping to Earth anyway. Particles are flowing down the magnetic field. And so they have a constellation of small satellites or CubeSats at Leo, kind of measuring the particles streaming along these magnetic field lines and mapping them out to figure out what the tail is doing. And they also have auroral imagers to kind of help supplement that and figure out, can we map certain structures and currents to certain dynamics in the tail. So these are kind of different ways you could try to study the same science question from very different approaches, very different regions of space, very different instrumentation approaches, and different budgets. Yeah, yeah. And actually, the latest Heliophysics decadal survey recommended kind of a large-scale mission to address this question, and they did it by combining two of these approaches. One is with lots of small spacecraft in different orbits in the tail to measure in situ what the fields and particles are doing. And then another kind of high inclination polar, high altitude imager to look at auroral imaging and energetic neutral atom imaging to really constrain all these different pieces. And so I think it's always good to kind of try to think out of the box of how can we actually probe these different systems in different new ways, especially if you are budget constrained or not. Yeah. Okay, so I think we're close to time, if not at time. So I just wanted to emphasize my takeaways if you like really spaced out for the past hour and a half, at least the things I want you to know about the magnetospheric system or geospace. One, that it's interesting both from a pure physics perspective, there's reconnection, there's shock physics, there's particle acceleration, but it can also tell us a lot about other systems, whether it's Jupiter or Mars, or more applied things, which I didn't talk about much here, but I think you will in the next lab, of the space weather implications of the dynamics of this system. How does it affect society, our infrastructure on the ground and in space? And then the other point is just that it is very complex and highly interconnected. So, my specific research area is Earth's radiation belts, but I can't understand them unless I understand the magnetotail dynamics and auroral dynamics and solar wind and what's actually driving the system. And so I think as magnetospheric studies are moving into this system of systems approach of everything is interconnected, and even if you know what one little starling bird looks like, knowing what the whole system is doing and how it's moving requires a lot more complex physics and models and data sets. Okay, thanks. Should we? Yeah. Yeah, so I have designed some missions that I would love to see flown. I personally, and this might be a bias, I think some in situ measurement is somewhat needed. I think the imaging tells you something about context and dynamics, but I think it's never the same as actually measuring the particles that are causing that emission. So at least if we go back to this picture, I think without these spacecraft measuring the local particle and field environment, just the imaging, I would miss out on a lot. So I think imagers combined with in situ, or I'm kind of personally a fan of multi-point in situ measurements, because I think that is where we're going with how this 3D system changes in time and space. We understand the little local single point measurements, but knowing what's happening here and how it changes here, to me is kind of the next question. So yeah, I would kind of put these spacecraft back here and then maybe distribute them also in local time, so you could get a sense of how particles come in from the tail but also move around the system and circulate through the whole thing. Yeah. I was on the magnetospheres subpanel. So I read a lot of white papers that were submitted and tried to summarize and consolidate some of the concepts. And then I've also, put in some smaller mission concepts, SMEX size, things like that, or MIDEX, contributed to those science teams. Definitely postdocs. Students, I don't know explicitly, they didn't state on their white paper, but I think there were some postdocs certainly just because I knew who they were. Yeah, absolutely. And you ask, and the reason I don't necessarily know is we didn't necessarily weight the name on this white paper more than this one. We collected all the white papers, all the concepts, all the science questions, all the mission concepts, tried to figure out what does the community want and what would advance the community on the magnetospheric side. Yeah. Yeah, you're absolutely pointing out one of my biases of space-based instrumentation. But there are a lot of ground-based tools you could use. Even just ground-based auroral imaging could really complement a lot of these in situ measurements and give the context. Ground-based magnetometers can show you plasma waves that propagate to the ground, so they can be used as a tool of what's going on, and especially if you can distribute them in longitude more easily than having spacecraft all over, you could see what's going on here versus over here and here. So I think the combination of those are great assets to combine with spacecraft measurements. Yeah. Yeah. I'll stick around through the short break. Yeah, and then
Let's take a 10-minute break.